This is our group submission to the Hack the Bay Challenge. To model water pollution, we explored how various factors are tied to indicators of pollution using data from the Chesapeake Monitoring Cooperative and Chesapeake Bay program, as well as supplementary geospatial datasets. The resulting model provides visibility so that useful predictors may inform timely decisions and inspire action to improve the health of the bay and its stakeholders. After reading about the Chesapeake's current issues, we decided to focus on predicting total nitrogen. We wanted to add to the novel findings of the linked June 2020 Databricks Hackathon that location-related variables were important in modeling water pollution, and we wanted to get more insights into the factors that may help to create location-specific solutions for water pollution management. We prepared and wrangled weather, land cover, distance, and air pollution data, then used the data to compare two models and refine our features to come to our final model. Details on data preparation, correlation, and missing value imputation are on our team GitHub, linked in the description. Using the provided dataset from CMC and CBP, we filtered for total nitrogen. Then we aggregated data by date and latitude and longitude, and took a mean of the measure values to obtain one reading for each day and each location that samples were taken. Using land cover data from the Multi-Resolution Land Characteristics Consortium, the National Land Cover Viewer, and the Watershed HUC-12 Boundaries Shapefile, we obtained the following features. Land cover percentage for each code in the NLCD legend. Some examples are shown here on the right. The mean of the pixel values for each segment, and the area of each segment in acres. We also obtained NARR weather data for the features listed on the right, and extracted this data for dates and locations relevant to each water pollutant observation. We created a feature measuring the distance from each sampling site to the outflow of the bay, marked on the map here. Another feature we created represents all NO2 pollutants from correlated point source locations and air monitoring stations in the airshed by year for each HUC-12 segment. We tried a variety of different models, including random forest, linear regression, CatBoost, and XGBoost, and narrowed it down to two final contenders, XGBoost and CatBoost. In the XGBoost model, we used relatively strict correlation grouping to eliminate redundant features, along with a KNN imputer for missing values and a robust scaler. We also tried a CatBoost model, which is great with categorical variables. CatBoost doesn't support date-time formats, so we created date delta as a numeric variable which captures the time in seconds from the latest record. This is so that we might capture a trend over time, instead of only seasonal effects using categorical variables like month, although we kept some of these too to look for seasonality. We combined developed land, forests, and wetlands into one combined feature for each of these types of land cover. We performed hyperparameter tuning on both models and compared the models' evaluation metric scores, shown here. The two models, depending on their strengths and limitations, included varying methods of feature selection, scaling, and imputing. While XGBoost might have had a smaller RMSE, the features weren't well explained by the SHAP plot. We chose the CatBoost as the final model, as it better clarified the predictors that were most important. Here is a SHAP plot for the final CatBoost model, which uses coalitional game theory to show us the contribution of each variable to the prediction, given this particular set of feature variables. Variables are listed in order of importance, with the most important at the top. The model shows that two main groups of predictors, among those that we tried, are important in a prediction of total nitrogen in the Chesapeake Bay: land cover type and location. Land cover type 82 is cultivated cropland. Land cover 9T is wetlands, and land cover 2T is developed land of any type. Variables marking location also were important predictors, in our case, both lat-long as well as the distance to the mouth of the bay. This models total nitrogen across the entire Chesapeake Bay watershed. However, we discovered hints along the way that creating two or more separate models for different distances from the bay may work even better. We recommend exploring this possibility as a next step. Our notebooks for both models are on our team GitHub, which is linked in the video description. Thank you to Hack the Bay organizers, Booz Allen Hamilton, CMC, and all water sampling citizens for making this opportunity possible to contribute increased clarity into the Chesapeake Bay.